Hello everyone, are you able to hear me? Great, great. Hi Sarvana, hi Jairam, hi Karthik, hello David, hello Tushar, hi Lloyd. All right, all right. Hi Lakshman. Brilliant. So everybody's ready, and I'm extremely sorry for being 4 minutes late. Generally, it doesn't happen. So doesn't do not assume that next time I'll be uh, again late. All right. So, all right. Again. So let's start. So in the last discussion, In the last discussion, we talked about big data in general and we gave an overview of the whole ecosystem. So, do you have any questions related to the previous session, which was yesterday? Hello, Sanjay. So, so everyone, do you have any questions before we move forward? All right. All right. So, if you had some questions related to the quiz which had some terminology which you did not understand, you could have skipped those questions, all right? Or you can simply skip them and then you can attempt it after today's session, all right? Correct, correct. Because our first session's discussion has become little bigger, that we discuss more into details about the ecosystem. Therefore, you generally have these mm, some of the questions. We will realign the quiz again, meaning we'll split the quiz probably. All right. All right. So you can attempt as many as you want. All the all the questions, all the answers will be recorded. Okay. So you can attempt as many times as you want. All right. Sandeep's question point is that can you please insist on QA session at end? Uh, that will be little difficult. So let me just start making notes. So this is something I'm not in a great favor for into, because if I keep the question answer session at the end, what would happen is that if you have some doubt on some topic which we are discussing now, and that doubt did not get cleared, there are high chances that you lose interest in rest of the topics. So instead, we will finish one topic and then I take up the quiz. I take up your questions. Okay. So we'll go topic wise. Does it make sense, Sandeep? All right. Because what will happen is, in case you got some question and I said we'll have QA session at the end, where you might become less interested in rest of the topics, thinking that my question is not answered and hence I don't know what is going on. All right. So we will answer the questions at the end of the topic. All right. So any more questions? Just a second. Probably there are some people who are trying to log in. and maybe they are not. All right, some people are trying to log in, so let me just help them out. This is one-time exercise, okay? And all right, I've sent him the mail. So any more questions, or should we start our session today? Great. So let's start with the today's session. All right. All right. Before we start the session, that'll be a little too long. All right. Yeah, that'll be a little too long. All right. So let's start with the session today. And good. So yesterday in the discussion, we talked about all these components. Now we will dive deep into each of them. Along with all these components mentioned on this screen, there are few more things which we will discuss as we go along, and such as Zookeeper, and such as few more NoSQLs which we will discuss as we go along. All right. So as we told yesterday, the Hadoop distributed file system is the basis for whole ecosystem. And as a matter of fact, there is no other alternative to HDFS as of today, which provides a similar kind of scale or uh, similar kind of resilience. Resilience as in the resilience to failures. Okay, in case some machines go down, still the system keeps working. So Hadoop distributed file system is something which we all need to understand very well. Now before we instead of I just enforcing my thoughts, we will do it in a in a discussion manner. All right, so let's start our discussion. So the question to all of you is, let's say you have to store 100 terabyte data. Your objective is to save 100 terabyte data somewhere. How would you store it? Okay. Let's say, in other words, all of you decided that you will build a great movie store in which everybody can store the movies. Now, and you decided that the total amount of storage we should make available should be around 100 terabyte. Now, how would you build such kind of a storage? Anyone? All right. Sandeep says save in chunks on distributed computer. That will be the final thing we'll discuss. Let's discuss, the traditional way without you knowing about Hadoop or HDFS. Okay. If you have come up with save in chunks on distributed computing, then it's just brilliant. All right. Okay. Sanjay says store in blocks in multiple days. Karthik says distributed computing. Now Tushar says To store 100 terabyte data, which is available to all, we can store them in a network file system. Brilliant, brilliant. Keep going. I want to see that. Lloyd says SAN, as in storage area network. Brilliant. Jairam says hard disk. And all right. Suresh says 100 SSD. And Rajesh says the RAID. Okay. Good. Good. Ravikant says over a network of 500 2 TB hard disk. Brilliant. Brilliant. So some of the solutions were pointing to already a system like HDFS, and the other solutions were pointing to something like this. All right. So build a network attached storages or storage area network. All right. In very simple words, if I have to do it earlier, the way we used to do it earlier, before I was introduced to these new systems, the way we build these storage is we have this. We bought 100 hard disks, and we would connect those 100 hard disks into various computers and make these 100 hard disks available in the network. Of course, there is a security. So we make these 100 hard disks available as folders in the network. If you've seen that you map a network drive into a folder, even in Windows and even in Unix or anywhere. So you map these 100 drives into a folder on various computers. And finally, we mounted these 100 drives into some main folder on few systems and told all the users that, hey, if you want to store your movies, you can use these 100 folders. Do you see any problem with this? So we mounted these folders on, say, multiple computers and told people that, hey, if you want to store your data, you can go to these any of these four computers, and there'll be a folder called main folder. Under this, there'll be 100 folders with drive 1, drive 2, drive 3, drive 4. All right. Now you can store the data. You can start storing the movies in these folders. You see any problem with this approach? Is this approach clear, or should I repeat it? All we have done is connected these, bought 100 hard drives, 100 hard drives. Then a hard drive is somewhere we store the data. So we bought these 100 hard drives, connected to my various computers, connected these computers in the network, and then made these network drives available as folders, as a network folders. And then we created a hierarchy in which we are showing that there is a main folder and there are these 100 folders where each folder is representing a drive. Brilliant. We have got extremely good points here. Sarvana says that if any computer fails, then it cannot be accessed. All right. This is nice. Yes. So Tushar says that these 100 folders will be visible in one place. That's correct, Tushar. David says unbalanced data. Brilliant. Brilliant. No backup. That was another point from David. Sanjay says that we should know which drive has which movie. Brilliant. And what if one drive fails? Good, Sanjay. Rajesh says that unavailability of fault tolerance. Good, meaning there is no fault tolerance. Himanshu says if the movie is more than 1 terabyte, we need to split on multiple drives. Brilliant, brilliant. And Suresh says that in case any system fails, yeah, we have. In case any system fails in between, then you're gone. Thank you, Suresh. This is also a very good point. All right, very good points. This is something we should think about. All right, the point Suresh made was in case we are reading a big file, say 1 gigabyte file, and the system fails in between. While we finished almost reading 1 gigabyte, the system fails or network fails. Lloyd says OneDrive fails, we lose movies, no redundancy, no load balancing. People might just fill up OneDrive. Brilliant, brilliant, good. With thank you, Vidya. If main folder fails, whole system fails. Now, Tushar says, I think the system would be kind of faulty at some point of time. Also, if one system fails during reading or writing, then it would be more time consuming. Brilliant. So, yes, all of these problems are this is the way I have summarized them. Okay. First is, what about failovers and backups? In case here, even if we back up each drive onto the same computer using a RAID is a way in which we basically copy one drive into another one on the same computer. Even if we do that, even if we do that, what would happen is what would happen is in case the network connectivity is gone, then the data is lost. Okay. Failover and backup, there is a slight difference between failover and backup. Backup means uh, backup saves us from complete loss of data, while failover saves us from availability of the data. Okay. Eventually the data might be available, but our users may not be able to access it. That is the lack of failover. Okay. In case one system fails, quickly we switch to another system. That is called failover. Right? How would you distribute data uniformly? Probably some of you have already covered this point, that the user might end up filling up drive 1, drive 2, drive 3, while drive 4 is completely empty, right? Because so let's say we decided upon storing on a movie on storing movies. So we came up with the idea, let's just store all the movies starting with A on drive 1, and let's just store all the movies starting with B on drive 2. Now you see the fault in this. Drive 1 might get filled up very quickly, while drive B, where the movies is going to start with B, are very few, and therefore drive 2 might be fairly free. So we are not able to distribute our data uniformly. Other problem with this is something which somebody has mentioned. I think Himanshu has mentioned. If the movie is bigger than the disk, we had 1 TB hard disk, and also we might have to split it up, and may not be able to store it in drive 1, right? Also, in case you are trying to store a movie in first drive, and the movie is of 1 GB, and the space available is 900 MB. So this 900 MB will be free, and we are not able to fit in 1 GB movie. So we'll eventually have to split the data. So, which means the current file system is not resilience, is not able to provide those kind of functionalities. Also, do you think it's a best value for money? You might be having a lot of hard disks or a lot of computers already in your organization, and can't you use them? The problem that would occur is, let's say there is a computer which is having only 20 GB of hard disk or 30 GB of hard disk, and you are trying to store a Blu-ray movie which is 80 GB. So you may not be able to use those kind of systems in this architecture. And the more the computers you have in this network, the more problems you would have to manage them. Okay. Therefore, we may not like to use our old computers or the computers we already have in organization. We might want to use the latest hardware. All right. So it doesn't look like it's a great use of money. Next is, but what about increasing accessibility? All right. Something which Suresh also pointed to, that in case some system fails at any point. Similarly, let's say today is Independence Day, and everybody in this environment wants to watch a particular movie stored on one drive. Now, when all of the people want to watch the same movie, the hard disk would crash. Reason being, hard disk is has the limited ability to handle the load. It cannot handle multiple requests at the same time. It is a physical hardware where the header moves from one place to another. So its availability is not really great. Only one person can use a hard disk properly at a time. Although theoretically multiple people can use, but if you look at it closely, only one person can use. Therefore, we have to think about how can we make it uh, tolerant to how can we make it tolerant to the accessibility. So so next point, which is scaling out, this is something which we all last 2 points is something which we all miss out on. The increasing accessibility, which means the velocity part of it. One part was volume part of it, as in how would we store it. Second part was velocity, as in number of requests when they start coming in a number of requests keep on increasing, then what do we do? That is the velocity part of it. All right, just give me a second. I need to see what's going on. Uh, some user is not a mic is not able to get in. No, the thing is okay because some user is having a lot of problem in joining, so that's why. Extremely sorry for this. All right. Anyway, I can't do much about that. All right. Next problem which we were about to discuss, is everybody able to hear me? So next point, the last one, is about scaling out. So everybody clear about increasing accessibility? What does it mean by accessibility? No? Yes, accessing the same data by. All right, brilliant. Now, the next point we want to discuss is scaling out. Scaling out means today you have a requirement of 100 terabytes. Okay. Tomorrow, what happens when the need keeps on growing? Every third day, today you have 100 terabyte, tomorrow you have 200 terabyte requirement, and so on. How easy is it to scale out? As in, how easy it is to create your own folder, more hard drives, and keep on adding them? Do we need to update at 100 places? Or do we need to come up with some new schema of design, as in some some movies in one folder, some movies in another? All right. So scaling out is a very important issue, and that's why if you look at the definition of all the components that are adopted by Hadoop uh, ecosystem, all of them have a criteria called scale out. When you are adding more machine into the ecosystem, you should not be so worried about uh, managing it. It should be very plug and play. You should be able to scale out or as soon as possible. All right, good. So to solve all these challenges which we just faced by designing our own system, people came up with something called HDFS. All right. Now, let me just go through first brief description and then we'll have the question answers. All right. Now, what exactly is HDFS? HDFS means Hadoop Distributed File System. Okay. It's a file system which is distributed. All right. We will go step by step while we describe what exactly it is. Now, it is made up of the whole Hadoop file system is made up of multiple computers. One of the computers we designate as name node. Now, rest of the computers we designate as data node. Okay, and the computer we designate as name node is somebody who would know which file is where. So name node is like somebody having the index of files. Okay, so name node knows that when somebody wants some data, where should he be redirected to, or where should she be redirected to get the data. The actual data, the actual data is stored on data node. All right. Let me ask you in a twisted way. If we do ls, how many of you know ls or dir command in DOS? Okay, assume that you are doing dir command, you're running dir command on HDFS. Okay, so when we run dir command, who will you be accessing? Name node or data node? Anybody? Name node. Brilliant, brilliant. So yes, great. Suresh Jairam Nandini. Now, so name node contains like a big index of your book, the way in front of every book there is an index. Similarly, name node contains the metadata, which is what is where, and all of these things. When we talk about name node, data node, these are not hardware. These are normal computers on which we are running these processes, the way your computer runs the mail server process, or your computer runs in background the http server or something else. Similarly, name node and data node are services running on these machines. So machine 1 is designated for name node, machine 2, machine 3, machine 4, machine 5 are your data nodes. All right. Now, is everything clear to everyone? Name node keeps data in the RAM in case, because in case you want to know about some file, name node will not have to look into the disk to give you the result. Although name node keeps all the data backup in the file system. Okay? In case name node crashes, you can recover the data from the file system. All right. So every data which is in a name node is persisted into the disk, but whole of it is kept into the RAM. Correct, Karthik. So name node and data nodes are programs in the machines and not the not the entire machine. All right. Any other questions? All right. Great. We have got some good questions. Let me go one by one. Sanjay says, does the name node have to be the most powerful CPU, RAM, storage in the cluster? Uh, Name node doesn't have to be very powerful with respect to CPU or storage, but RAM wise, it has to be powerful. It has to have good enough RAM and okay types, uh, okay-ish CPU. It doesn't have to be 100 cores. All right. So Lloyd is saying, can you elaborate on is a service like for calling applications? All right. So can you elaborate on is a service? Basically, whenever there are some programs which keep on running in the background continuously, listening to the network calls, as in the way when you connect it to a website, you are hitting a web server which is running on a port 80 and responding. In the similar manner, every service generally runs on a network port, listening to the incoming traffic and responding to it. In the similar fashion, name node and data node work, all of these are basically services. Tushar's question is, I am a bit confused. Name node keeps data in the RAM or file system. Answer is both. Okay, so if all whole of the metadata is kept in the memory as well as in the disk. Now Richard's point is, if machine 1 fails, name node can shift to machine 2. That we will discuss in detail. Very good point, Richard. I will take a deep dive into what happens in case name node fails. All right, we'll go into the details. Suresh, you got the answer? Tushar, you got the answer? Vidya says, won't the whole file system fail if name node goes down? That's correct. We will go into the details in a minute. All right, brilliant questions. So good. Sandeep's question is also the same one. Now, Jairam's question is, what would be the minimum hardware requirements of name node and data node? So minimum would be as per the Cloudera and Hortonworks is something like minimum should be 2 GB RAM in name node. Okay, and data node it's okay with 1 GB, but data node need to have more hard disk because it is going to be your storage horse, right? So it's up to you. Rest is up to you. All right. So Sanjay's question is also with respect to the name node backup. Good. So almost all of you have next question as what happens when name node fails. We'll come back to this in a minute. All right. We'll go into a little bit more details and then we will talk about what happens in case name node fails. Yes, Tushar, that's correct. The metadata is stored in file system first, and whenever a request comes to access some data, it's loaded into the RAM. So it doesn't wait for request to come to access for some metadata. It right away loads it as soon as, so whenever you are creating a folder. Okay, let's say you are creating a folder. Creating a folder is effectively creating metadata, not the actual data. But when you are creating an empty file, then also you are creating only the name node. Okay, not the actual data. Now, when such kind of metadata is getting created at name node, okay, when such kind of data is getting created at name node, what happens is that this metadata gets persisted into the disk as well as loaded into the memory as soon as it gets saved into the disk. That's how it is maintained. All right. Now, Sanjay's question is there a limit to scale out on data nodes based on the configuration on admin node? Very good question. Very good question. So, Sanjay's question is if we keep on increasing the data nodes, or if we have more and more files into the system, the metadata will keep on increasing and it might hit the upper boundary of name node. That's a brilliant question. So we'll go into the details how to counter that and what do we do in such cases. All right, great. Moving ahead. Now, the next thing you should know about is in order to have the uniform distribution, every file is split into a chunk of 128 MB file. Okay, every file is broken into 128 MB blocks. All right, let me finish this slide and then I'll take up the questions. So but that doesn't mean you don't ask questions. You keep asking questions. So if there is a file of 1 GB, it is broken down into 128 MB blocks. Now, some of you might be wondering that we heard about 64 MB. How come it's 128 MB? It's some kind of a design decision in Hadoop 2.0 as well as in Hortonworks. Um, in Hortonworks uh, version that the default one is 128 MB block, but you can change this size. All right, you can change the size per file as well as for the whole file system. The default size you can change. So the files are split into a chunk of 128 MB blocks. It helps fitting the big file into small disks. It leaves less unused space on a disk. It optimizes the data transfer. And the most importantly, it distributes the load to multiple machine. Now you can imagine that if there is a movie, 1 GB movie, and we have stored it is broken down into 8 parts. Okay, 1 GB movie is broken down into 8 parts, which means 8 people can actually watch the movie parallelly if they are just there is a phase difference between one person to another of 128 MB. So if I am watching from the beginning, you are watching after say 10 minutes, so you might be reading the data from another data node, and I'm reading the data from another data node, which means that multiple people can concurrently watch the movie. Make sense to you? So we have suddenly increased the size, suddenly increased the availability to about 8 times, right? That's why, and in case your movie is, in case you have many data nodes and you want to have more availability, you can bring down the block size to smaller one, and 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 make it available more. And we will talk about accessibility. How do you increase accessibility of a particular file further again? All right, let me take up the question now. Good. Richard's question is, so does all data flow through name node first? Okay, where it changes to be more st- structured. Good, good, very good question. So Richard's point is, does all data flow through name node first, where it changes to be more structured? So no, the name node, the data doesn't flow through the name node. That's the next slide we will come up, and you will understand why and how does it happen then. All right. Next question is, what is the minimum size of the data for HDFS? So, okay. So minimum size of data can be anything. Okay. Suresh's question is, what is the minimum size of data for HDFS? Now, do you mean that what is the minimum for how much small data should we be using HDFS? Is that your question? All right. All right. So it's not something it doesn't mind even if you have no data at all. All right? It doesn't mind. It's up to you to decide when to go for such kind of system. All right? It's up to you, because if you are just dealing with few terabytes data, maybe 2 terabytes data, it may not sound sensible to have multiple machines. Okay? So, but that's a call when you think about the availability and all the questions which we just discussed, that we face these problems in the network file system. If you face the same problem even for 1 terabyte data, then probably you should choose HDFS. Reason being, your accessibility patterns are forcing you to move to a distributed file system. All right. Now, Shravana's question is it 128 MB or 64 MB? I think for Cloudera version, they push 64 MB block size by default, and Hot and Work is putting 128 MB by default, but it doesn't make much of a difference. You can change it when you are installing these. Okay, these are minor design decisions. Sanjay's question is, Sanjay's question is, does small block or large block work well with big data files? So, of course, a larger block is better. Reason being, larger the block, smaller the metadata. If you have, let's say, your file is being broken down into 16 parts. So suddenly your metadata is increased by 16 lines, meaning part 1 is on this machine, part 2 is on this machine, part 3 is on this machine. So this way, if there are 16 parts, there will be 16 entry at metadata level, right? So bigger the block size, lesser the metadata, and lesser the mobility, and difficult to fit in. So, and smaller the files, more the metadata, and and I mean more time to switch between the machines. Okay, so because when you are gathering a file, you will have to stitch it through multiple data nodes. right? If it is very small, your most of the time will go into stitching and switching between the systems. So you have to keep sort of a heuristic number in mind, a number which says that okay, this is the smallest file which we are kind of expecting that way. Next question is, so I hope I answered your question, Sanjay. All right. Vidya's question is, does the kind of hardware added depend upon volume, velocity, variety is increasing? Question on scaling out. Okay. Okay. So question from Vidya is, what kind of hardware we need to add, whether it depends on velocity, variety, and volume. All right. Now, so we will keep variety aside for time being. Okay. We'll only talk about volume and velocity. If you have more number of requests coming in simultaneously, then you will have to have a better hardware and uh, name node with a better RAM. We'll see why do we require, and also more number of data nodes. So more number of data nodes will be able to cater to more number of users. All right. As well as more number of data nodes will be able to handle more volume. So therefore, we, and as a thumb rule in most of the big data systems, whenever we talk about big data solutions, all of them work on commodity hardware. None of those systems say something very explicit, like something like we want at least 10 gigabyte of RAM or 100 gigabyte of RAM. No, they say it's okay to have a smaller RAM, a smaller normal, like 16 GB RAM kind of thing. So, or maybe 8 GB, 4 GB. It's okay with most of these systems. All right. Nandini's question is, can you explain how transfer is optimized again? The transfer is optimized in this following manner. In case one data node goes down, the data that has to be transferred from this data node is in the blocks and it's easier to move to multiple machines. All right, that's how it helps in transfer. So balancing the file, moving these blocks is easier than moving the complete file. And somebody, probably Suresh, said earlier, I'll use his answer to answer your question, Nandini. So Suresh was saying that in case, let's say you are trying to download 1 GB file, the chances of 1 GB failure is higher in case you're downloading the full file, right? But in case you're downloading the data in blocks, in case one block did not complete successfully, you can try it again. Therefore, it optimizes the transfer of data. Make sense, Nandini? Now Suresh's question is, what will happen if many users are accessing the same data node? Again, if many users are accessing the same data node, then that data node is getting thrashed. Okay. In those cases, you will have to come up with the topic which we are going to discuss next, which is increase the replication. All right. We'll discuss it after this. All right. Ravikant's question is, what happens when we lose data? What if we lose one data node? And how does name node know about it? And also, how does name node work around the data lost from data node? Brilliant. Probably all of us are saying that. Let's move to the next slide. And Ravikant, you will get the answer immediately in the next slide. Okay. Now, Jairam's question is, what if we have 100 petabyte data? How many name nodes and data nodes are required? For 100 petabyte data, you can just divide it. So generally the way it's configured, the data node service, the way it's configured, whatever hard disk is there on the data node machine, it utilizes around 80% of that hard disk. Rest of the 20% of the hard disk is dedicated to the local machine. Okay, so because every data node is at the end of day is a computer, it has operating system, it has local file system as well, and that local file system is what is storing the actual data, right? So therefore so you can do a little bit computation that this is the money we have, and these are the existing systems we have, and therefore we can buy these many machines. So you can think of, let's say you have 100 petabyte data, which means you will have to have at least 100 data nodes, and this calculation we'll have to do again after we understand the replication. All right, let me just go to the next slide, and then we will discuss these last 3 4 questions again. Now there is a twist to the story. Every block which we created earlier gets replicated, meaning there are, for each block there are two more copies in the network, and these copies are on different servers, which means every one block is available at three different locations. Okay, by default the this is 3, but it can be changed to anything on per file basis, as well as you can change the default behavior. Now no two copies of the same data is on the same data node. Now, what happens when data node fails? The lost blocks. So as soon as data node stops responding, admin node figures out, because it did not get a ping from a particular data node. So if it doesn't get a ping from a particular data node, for some time it assumes it to be dead. Okay, it assumes it to be dead and hands over this, figures out, okay, this data node is lost, all the blocks of this data nodes are lost, and where all do we have the copy of these data nodes, the replica, where all is it available? Now it instructs those data nodes which contain the replica copy to start replicating to some third node, so that the replication factor is brought back to 3, because after the loss of a data node the replication factor goes down to 2, because out of 3 one is lost. So the replicate to it instructs the data node which contains one of the copies available to start copying or duplicating the data to another node, duplicating the block to another node, to bring the replication factor back to 3. All right, now if you notice that traditionally we had been only taking up 2 backups, but here by design we are taking up 3 backups, right? Or let me put it this way. Earlier we used to take only single backup. Now we are taking 2 backups, meaning total 3 copies. Earlier we used to, in our everybody who has been used to database management, we generally kept 2 copies, one current, one previous, and so on. Here we are keeping 3. And the reason is that your file is broken down into pieces. If any piece is lost, the whole file is lost. So probability of losing data is really higher. And the loss you will incur in case one data node is lost completely, right? The loss you will suffer due to a loss of a single block is really high. That's why the replication factor is little above 2, which is 3. Okay, so this is how the replication work. Probably that explains your questions. Do you, all right. Now let me answer your questions. Now Jairam, now you can see that for storing 100 petabyte of data, you will have to build a storage of 300 petabyte data. That sounds like a waste of storage, but that's the truth. Okay. Now, coming back to your questions, Sanjay says, does the metadata indexing on admin node a dynamic process which adjusts based on the incoming velocity of the data? Uh, so, so what it's a complicated question actually. So when the request is coming, generally admin node does not behave like a last elastic one. It does not change its behavior based on what kind of velocity is coming in. All right, it generally remains the same no matter how many requests are coming in. Okay. All right. So so it doesn't change the behavior, it remains the way it is. The more and more data is coming in, it makes a note of those and keeps on building the metadata. Right? So Richard, you got the answer to your question. Doesn't the three replica consume more of limited space, therefore increase the cost of more hardware? No? Great, great. Sharna's question is, if the data node not getting response from uh, data node immediately, it will prepare for replication or it will try to get response for some time. Correct. So if a user is not getting response or name node did not get a response from data node for some time, it will assume it to be dead. Okay, and then it will delegate all the requests to other machines which contain the copies of the data, and in the meantime it will start the replication as well. Sanjay's question is, are the copies of data compressed? All right, it all depends on how do you want it. You can tell HDFS to use a particular compression because compression is enabled and is a part of HDFS library. You can enable an HDFS compression, and and you can, while sending the request to HDFS, you can mention as part of the request parameter also that we want it to be compressed. All right. Now Karthik is saying when data node fails, it is copied to the new data node. But is the request serviced? Yes, request is serviced because we have copies of data, right? I mean, imagine this. There was a file which was on data node 2, 3, and 4. Now 2 is dead and request is coming for the same file. We still have the copies of those data on 3 and 4. So request might go on 3 or 4 while it's being still copied onto the fifth one. Okay, brilliant. Good question. Now, this is a question from Shravna. If name node not getting response from data node immediately, it will prepare for replication or it will try to, no, it will not keep on waiting for some more time because it has already waited enough. All right. If, and then it will start replicating. All right. So Vidya's question is, does the name node be set up to increase the replication factor when a certain data is accessed more, even if data node has not failed? Brilliant question. So the question, I think some Suresh also asked the same thing, that does name node increase the replication factor for those movies or those files for which there are more requests? um, there are some versions of HDFS. I think the Qbol one. There is a company called Qbol, and there are some other ones also which have tried to implement the same thing. Okay, but by default, HDFS doesn't do that. So Sanjay's question is, so it serves one request at a time. Yes, one request for a file at a time. Okay, so it basically tries to be strongly consistent, meaning if there is a particular file which is being accessed by one thread at a time, it doesn't let it alter. Okay, read and write request cannot go together at the same time, and that's something name node makes sure it is very strongly consistent, because in case of file system we cannot risk the consistency. Now Suresh's question is, in what form data gets replicated, file by file or like an image? So it's by file on file. I mean, it's block by block actually. Okay, so if you look at the data node, I'll show you the data node, and data node will have these strange file names for each of the blocks. So it doesn't make much sense. Those blocks would not make much sense to end user. S- But these blocks are being copied instead of the full file being copied. Okay, so the minimum unit of communication is this small block. So Sandeep is saying that, is name node responsible for scaling? Yes. Karthik is saying, all right, yeah, we have Sharna's question. Will the rack be considered while using or taking the backup? All right. So this is something called data locality optimizations, where the rack and rack awareness comes into play. And we do not, HDFS builds its own backup system. It would not consider much about, okay. All right. I think I got your question. I got your question. So Sarvana's question is that, let's say, let me reframe your question, okay? So, on which machines will these three replica go? Okay? On which machines will these three replica go? Okay, first copy will be on on the same rack, and the second copy would be off the rack. That is the only thing which HDFS enforces. That first copy has to be on the same rack, meaning the same network, local area network as the main data node. So now there was a block here. We created a block here, and we are, so first copy, the out of three copies, first copy is generally on the node which is very closest to the incoming data. Okay, the first copy will be there. Second copy, sorry, first block, or you can say the original copy will be on the node which is very closer to the user, the original copy. Now first copy of those blocks will be on the same rack. Same rack means on the same local area network. I mean, same subnet, where only the last digit is changing in the IP address. Okay, so it'll be on the same rack. Same rack means every rack behaves like a small hub where only the last IP address changes. Now, third copy will be off the rack. All right, good question. Thank you, Shravna. I hope this is what you meant by in your question. All right, Himanshu's question is, if node 1 is down and replication is going on to another node, say node 2, good. What happens when node 1 becomes available again? Brilliant question. So again, the reconciliation happens. So let's say there was node 1 which went down, and after some time you realize, oh, this node has gone down for some reason, and you went ahead and restarted the machine. Now node 1 is back. It already has some data. The reconciliation process starts. As in, okay, this node has come back again. Has there been any change since the time the node has come again? There is a hash which is kept along with the data, which with the signature of the data, and that signature is checked whether it's the same data or it's has there been any more changes. So after reconciliation, a minimum amount of transfer is required in order to bring the node back. And also we will drop one set of data if one data node is one particular file is having 4 copies, one copy will be dropped. All right. Good question. Now Lloyd's question is, will the blocks be encrypted when transmitting over the network if there is a sensitive data? Okay, so that is something a responsibility of the end user. Okay, they can store their data in an encrypted format. Also, this communication between the machines is over SSH, which is fairly secure. All right, there is a protocol called secure cell, and which happens, I think, over 22 port, and the communication over that protocol is fairly safe and fairly fast. Good. Now, Sanjay's question is, after a file is processed on a data node, is the data node freed or initialized for the next request? If a file is processed on a data node, is the data node freed or initialized for next request? I did not get that. So data node is right now not processing anything. It's just storing the data and responding to the requests which are coming from the name node. All right. And all right. Okay. So did I make any sense to you? If a file is processed on a data node, is the data node freed um, or initialized for the next request? I'm not getting this question. All right. If you can you rephrase it, please? Now there is a question from Karthik. It says, let's say there is a file which is having 5 blocks. Are there any chances that master copy of each block is placed in different data node, or master copy of all 5 blocks are placed in same data node? Good question. So let's say there is a file which is having 5 blocks. So it's not necessary that all 5 blocks, the first master copy will be in the same node. No, it will all be based on the space allocated by the admin node. Okay, if let's say data node 1 only had space for 1 block, it will have only 1 block of that new file, and rest of the blocks might be spread across the whole network. Good. Jairam's question is, what if name node fails? Just give me some more time and you'll get the answer. All right. Now Sharna's question is, if the data node is going down, the replication happens only for current accessing block or all the block residing in the data node? Yes, for all the blocks residing in the data node. So his question is that if the data node is going down, the replication will happen only for the current accessing block or all. It will be for all. Okay. So Sanjay's question is, so no processing is going on data node. Not right now. The processing will be done via something called yarn, and that we will discuss again. So with respect to file system, no processing, not much processing happens at the data node level. All right. Now, Priyabrat's question is the data node can be in different location? Yes, definitely. Data node can definitely be in a different location, completely different location. Yeah. So, Sarvana's question is, what if it comes back again, right? Now, let's say there's a data node that is going down. And so the moment a data node is not accessible, as in it has not responded to the ping, the copy of all the lost blocks, it will assume that all the blocks are lost. Copying will start happening simultaneously. But in the meantime, if the data node came back again, so quick reconciliation will start happening, and the new request, new copies might get stopped. Okay, or the older data might get deleted. It all depends upon how much data it has been copied and how much data is available right now. All right, very good set of questions. Only if we could create a sort of blog out of all of this. It's just brilliant set of questions. Pratibha is saying, when data is copied to a different node, will the name node be aligned to repoint the data to the new machine? Yes. Of course. So if the data is being copied to a different machine, immediately name node will make a note of it, and unless and until the copying is successful, it will not commit it. It will not say final. All right. Now, any other questions before we move? Okay, we have one more question from Richard, which is, does any of the data get lost if a node goes down? All right. So, Richard's question is, does any of the data get lost if the node goes down? How does it copy so fast right after the machine dies? The answer is it doesn't. It doesn't copy fast. The only thing is, when a block is getting lost because of a loss of a data node, same block is having two more copies available in the network. Using those copies, a third copy is generated, so that we have replication factor of 3, which means the block is again recovered to a total number of copies of the block has again become 3 instead of 2. Make sense, Richard? Now Karthik's question is, which program is responsible for replication and reconciliation? For replication, it is the data node. So name node instructs data nodes to start copying the replication. Similarly, name node asks data nodes to do the reconciliation. Okay, so name node tries to basically keep itself as much as free as possible. All right. So the process is generally started by name node. Name node takes most of the calls, and name node delegates pieces of works to the data nodes itself in order to keep itself free. Brilliant. Now, okay. Sanjay's question is, so seems like HDFS is for data storage of files, but after the request is processed on data node, what happens to the file on the name node? Is it deleted? So yes, HDFS is for the storage of the files. That's correct. After a request is processed to the data, what happens to? So there is no data at name node. Name node only contains the metadata, which is information about which file is having how many blocks and which block is on which data node, which file is in what folder, and which file is having low replication factor or good replication factor. That kind of information is there on name node. So what kind of file data you're talking about on the name node? All right. Now, what happens in case the file is deleted? So we tell name node to delete the file, and it will basically remove the entry and instruct the data node also to delete, drop those blocks. Okay, so that's how it happens. So Sarna's question is again, in case one data node has just shut down and come back again, will it have the fresh data, or uh, okay, so again, there will be a reconciliation to figure out whether what blocks of data have the same signature as the current ones, and therefore what nodes can be used as such. Okay, what data, what blocks can be used instead of recopying them. All right. So there will be a reconciliation as soon as a node comes back again. So metadata knows, name node knows that what files were there on this particular data node, and out of those files, how many of it are still intact. Okay, there will be a redundancy check, and then it can quickly say that okay, the data is intact, and then we don't need to keep on copying. We can stop the copying. All right, makes sense, Sarvna? Yes, Sandeep's question is, so incoming request is handled by name node and the reply is from the data node. Yes, that's correct. Let me show you. So generally the way we believe is that the request is coming to name node and then going to data node. No, that's not how it works. The way it works is there is a user there is a user who talks to the client driver. Okay, there is a client library which goes to the name node. Name node asks the client driver to talk to the individual data node. Okay, while there is a communication happening between name node, like in the terms of heartbeats, the data nodes are sending heartbeats to name node, but the user does not retrieve data through the name node. User retrieves data directly from the data nodes. If there is a file 1 which is there on 3 machines, the client driver will gather the data from these 3 different machines, okay, and and therefore it will not directly, just a second. All right. So the data which is coming here, or the request for storing the file will basically, after talking to name node will instruct the client driver that please go to the data node and talk to the data node regarding this particular data node and this particular block ID. Okay, so basically name node makes sure that the data does not get transferred through the name node, because if there are 10 more clients and instead of they utilizing the bandwidth of data node in between them, if every request or every data is going through the name node, the name node will become the typical bottleneck. All right, just a second. Hello. Yeah. Now there is a question from Lakshman. In that case, is client driver responsible for data assembly? Yes, client driver is the one who is responsible for splitting the data into blocks or stitching the data back into a single file. It is the client driver who is responsible for that. There is a question from Shravana. Once the client is done with reading writing, will it confirm to the data node or instead data node will confirm to the name node? Data node will confirm to the name node. Okay, let me repeat what Shravana is saying because that's a very good point. So when the client comes to name node that the client wants to write the data, name node makes a temporary entry saying this user has shown an inclination to store this particular file. Now, once the client driver is done with writing the data, the name node gets the information from the client driver as well as the data node that this block has been written. And name node, after taking these confirmations, mark the temporary entry as permanent. All right. So that's how it works. So Himanshu's question is, does this also mean that client driver is responsible for aggregating data and also the data blocks, sequencing the data block? Yes. So name node tells that data block 1 is the first block, data 2 block 2 which is located on some um, uh, so block 1, block 2, block 3, the sequence is given by name node to the client driver, and client driver retrieves them from all the data nodes and then assembles it and gives back to the user. In certain cases, let's say you are building a video streaming service where you do not want to assemble the whole video, but you want to serve the data in chunks. In all those cases, you will build a client driver which doesn't assemble. Instead, it streams the data as and when it is in an order it can play. Okay, the user goes to the client driver and says give me the data from this byte to this byte, and client driver asks the name node that okay, where does this file and this byte to this byte exist, and it tells the client driver go to the data node this one, and this keeps happening all the time. So that's how the client driver works. Make sense, Himanshu and Shravana? Ravikant, are you clear about client driver role? So overall thing is that instead of user as in you, talking in terms of metadata blocks to the name node, you will talk in terms of file, right? The the underlying work of collecting the blocks and stitching them is something abstracted to you by, ouch, you are abstracted from that complexity. All right. So that complexity is handled by the client driver. All right, brilliant. He got it. And all right, Lakshman's question is maybe I'm jumping ahead, but I thought application master in Yarn will do the assembly. No, he will do the assembly. We will discuss it. You will understand at that point of time. The Yarn, the processing engine, will try to represent it in the format which can be passed. Okay, application understand whether the data is JSON, movie, or anything. Here, HDFS doesn't care about what kind of data is it. Okay, the client driver doesn't care about whether it's JSON or it's a HBase data file or it's the XML, or it doesn't care. It just cuts the file and puts it into data nodes. And assembling it and parsing the file is the responsibility of Yarn. Yarn will be using the client driver to get the data. All right, I hope you will get it. The computation engine like MapReduce and all those will use the client driver to get the data. They are all the users of it. Now Sanjay's question is, in case of failure on the data node, name node does the reconciliation and again has to inform client driver of the change. In case of failure on data node, okay, name node does the reconciliation, okay, and again has to inform client driver has to, so that the client driver has to go no. So in those cases, let's say name node doesn't know that a data node has failed, okay. In those cases, and name node has told that okay, go to the data node 1, retrieve the data. In those cases, client driver will get an error. In those cases, client driver will do a retry on name node. And by that time, name node would know that this particular data has failed, and therefore it'll give you the fresh information. Right? I hope that makes sense to you. So the question is that if there is a communication gap between name node and data node. So name node gets information after maybe few seconds, around 3 or 4 seconds. Now at second number 0, name node thought that the data node is alive and inform client driver that go to the data node 1 to get the data. And in the same time, Namenode also told the driver that the same copy of the data is also available on these machines. Now it's the driver who will take the call that okay, I could not access the data node 1 for reading the block 1, so it will go to data node 2, which contains the copy of the same block which it could not access, and will read it from there. So this client driver is heavily resilient. All right. But next time, if the client driver comes in after some time, by that time, name node will be updated and it will get the correct results. Sanjay, did it make sense to you? Now, Karthik, question is client driver something like an application or a program in the command line trying to do? Correct. There is a command called Hadoop FS. That's a command which we will be using which will as our client driver. Also, you can write your own client driver, but that is something that requires a lot of work. All right. So client driver is installed on all the nodes in the machine, as well as if you are operating on your local machine, you can install the client driver on your local machine. You just have to tell the client driver the address of the name node. That's all. All right. Is that clear, Vidya? So client driver is like a library. It's not something like a server which is running. Okay. It's like a command. So you will say, you as a user will take this command called Hadoop FS and you will run it, and it will talk to name node and it will give you the results. Great. All right. The same thing is depicted in these diagrams. So the client who is reading the data goes to the name node and tells the name node, give me the metadata. Then it reads from the individual data node. When the client wants to write something, it goes to the name node and name node informs them that, okay, you can go to this rack or that rack and read the data. In the meantime, there might be a replication going on as soon as you write the data. All right. And the metadata looks like this particular data has 3 copies or 5 copies or whatever. The same thing is depicted here again, that client comes in, talks to the distributed file system, talks to the name node, gets the information about creating a file, and then it goes to the data node where it creates the actual file that gets replicated to other data nodes, and then it goes back and commits it. It tells name node that whatever I told you earlier, I am done with creating it, can you please commit it. All right. Now in the similar fashion, when the user is trying to read a file, it first goes to the name node. Name node responds back with the list of blocks and all the blocks locations. And then this HDFS client, basically these libraries, will talk to the data node, assemble it for you, and give it back, and then close the connection. All right. Now this was the anatomy of file write and read. Overall idea is that name node is only consulted. Name node is not somebody who transfers the data. A name node try itself to remain fairly free by delegating work to data node. All right. Now, from all of this discussion, we have realized that name node is fairly a single point of failure. Now, there are multiple ways to handle this. One is to keep the data safe, meaning backup of the data. So, name node can write to the multiple storages. Name node writes something called whatever data it has. It basically has the information about how many blocks are there in, what are the files, what are the folder names, and for each file what are the blocks, how many copy of these blocks are there, and on which machines is the each copy. So that is called metadata, and that metadata is stored in the disk in the form of namespace image as well as the edit log. Okay. Edit log is that which file has been modified, which file has been changed, that information. So these two sets of data is first kept as in the local storage as well as in some other storage. So name node can be configured to save this data at 2 places. Now in case name node goes down, we can recover our data from either the local storage or from the network storage. So this is not a great peace of mind, because it does give you the backup, but it doesn't give you the complete failover. Okay, it doesn't give you the complete failover. Do you want to take a break? All right, let's take a quick break, and then after the break we can discuss rest of it. All right. So let's start now. All right. So should we start now? All right. All right. David is back. Sarvana is back. I think everybody's back. All right, Rajesh. No problems. Good. Great. Now, the problem with single point of failure we were trying to describe that keep a backup of the metadata in the local storage. We are anyway storing the metadata in the local storage. We can also keep the metadata in a network file system. So name node was always providing this functionality of keeping backup in the network file system. All right. All right. So Vidya is saying that could you please take an example and run it through the component so that we have a better understanding of the Hadoop architecture. We'll go through that also. Right now, main agenda here is that what happens in the case where our name node goes down. That's the point we are trying to figure out. What happens when that single machine is down? All right. We'll go through one example where we will go through Hadoop architecture again. All right. So one way is to keep the backup of metadata at two places. All right. Second way is to have something called secondary name node. All right. Although secondary name node sounds like a great idea, but it is sort of a misnomer. It isn't really a secondary name node. Okay, instead it's just another computer which is having an updated metadata, and after preparing this machine we will have to manually bring it live. Okay, we'll have to bring it. Let's say there is a name node, there was an name node is down, there was some problem, it's not coming up, it was attacked by a virus or something else happened. Now, administrator has to prepare secondary name node. Secondary name node contains the metadata, but administrator has to intervene and turn on the secondary name node manually, which means there will be a downtime. Okay, so next strategy about defending against single point of failure of name node is having a high availability. This is something which is strongly recommended in any practical name node. In any practical scenario where you are going to store some amount of data, you should always have high availability setup. High availability setup means, so we all understand that there is a name node, then there are data nodes. We store the data in data nodes. We store the metadata in name node, and so on. Right? In case of high availability system, in HDFS 2.0 onwards, there is an arrangement which was made in HDFS itself for high availability. So name node can be configured with multiple standbys. Right now we are only demonstrating one standby, and this standby has the data as new as name node. So every time name node changes anything, it informs the standby. Similarly, all the data nodes, when they are informing name node, they also inform standby. So everything what is there on name node is also there on standby. Now, when the client library can quickly switch to standby in case name node is down. That is one of the great designs. Okay, it's called quorum general manager, meaning quorum is generally kind of an election. So if there are multiple standbys, name node and multiple standbys, based on the election, the primary name node is elected out of them, and that caters to the end user. All right. So this is probably the best form of failure, form of backup to avoid the single point of failure. Is it clear? Do you have any questions on this? So you can see that there is a name node, then there are standbys. Name node is talking to standby, backing up its metadata. Similarly, whatever data nodes are informing to name node, data nodes are also informing to standby. No questions? Yes, standbys are on different machine. Okay, that's correct. Vidya, are you on the same page? Lloyd is saying, is it as a synchronous process? No, actually, it's a synchronous process in the sense that both of them will get information at the same time, and the data is not committed by data node unless both of them are updated. Great. Now, Shravana's question is, so in this case, data node will be busy most of the time to respond to main name node and standby nodes. Yeah, that's correct. So only in the case of writes, only when data node is changing anything, only in those cases, data node will have to report to both name node as well as standbys. Okay, so it won't be that much busy as it looks like. But good news about data node is we can add as many data node as we want so that their headache is less. They can be data nodes can be easily scaled out, meaning more and more nodes can be added. Now Sanjay's question is, in case standby itself fails. Okay, good question. Let's say standby fails, then it doesn't matter. Name node is anyway running. Immediately you get admin gets an email that standby is down. Please make it up. In case standby is down, in those cases, data node will anyway function correctly. All right. So it's up to you how do you want to cater to this scenario. In the quorum, what happens is if there are three nodes, two standby and one name node. Okay, so failure of less than 50% is okay, meaning out of three, two nodes cannot, two of the three should not fail. Okay, we'll again discuss about the quorum part, but in case of high availability, in case standby goes down, everybody gets informed that okay, standby is down. And also in the in case of the high availability model, data node starts giving error that it could not write to the standby. Okay, it could not write to the standby. Therefore, based on your configuration, the system might turn into read only. Okay, might turn into read only, or it might continue happily. It is up to your configuration. How do you want to do it? Now Vidya is saying, so standby also must have as big a RAM as name node. That's correct. Because it might have to change, switch at any point of time. Now Lloyd's question is, can we do conditional routing? Writes are going to the name node and reads are coming from standby. Brilliant point. So in case of MongoDB, the writes keep on going to the primary while reads keep on going to the secondaries. All right. But here, since HDFS is highly consistent system, it does not allow that. As per design, it wants to be strongly consistent. What does it mean by being strongly consistent? Let me explain. So when we say strongly consistent, it means whatever data is there, it is visible. If imagine that we are writing to the name node, but we are reading from standby, what would happen is there will be a time delay between what we are writing and what we are reading. Therefore, the system will behave a little inconsistent. You are writing something, you are reading immediately, and it's not there, right? Therefore, that kind of design is not there, right? And it's not something they want to do. All right, makes sense, right? All right. Vidya's question is, does standby also hold all of data in RAM? Yes. It behaves exactly like an unnamed node. And at a point of time, you will not realize which one is name node and which one is standby. Because if name node went down and it came up again, name node will become a standby and standby will remain the name node. Now Shravana's question is, who will decide which standby to choose as main name node? So initially you will decide that okay, this node is okay, but after a point of time it will keep on switching by itself. In this there is something called elections as well. So quorum elections we will consider little while later. Okay. Now, Karthik Krishnamurthy's question is, where are all these things configured? I mean, which machine will be name node and which machine will be standby? So initially, the client library which accesses these will be accessing through something called a zookeeper. That will be a layer called zookeeper, and initially we will mark in the zookeeper that this is the name node and this is the standby, and later on the switching will keep on happening by themselves based on who is more available. Now Sanjay's question is, standby should be the minimal, same, better, it should be exactly same configuration as the name node. Make sense to you? All right, all right. I hope I am able to answer your questions. Please feel free to ask again if there is a doubt anywhere. All right. Yes, machine specifications of standby and name node have to be identical. Assuming that there are no more questions. So Lloyd's point is this offered by Cloudera distribution? No, it's a part of the basic Hadoop where no matter whether it's Cloudera or Hortonworks, everybody has to provide this, will provide this actually. Okay. After Hadoop 2.0, this is what has happened. All right. Going ahead with further. Now, I think Sanjay or somebody was asking this question. What happens when we keep on increasing data and we cannot fit it into the name node? What happens in those cases? In those cases, the HDFS 2.0 has come up with a feature called HDFS Federation. Federation means delegating work to different parties. Okay, so in those cases, the possibility of having multiple name node has been implemented. Okay, so for different folders root level as in after the slash, the top level folders can be configured for different name nodes. So any operations which are happening on slash my data one slash something else will go to name node 1, while for slash my data 2 slash something would go to node 2. Okay, so this way name node 1 and name node 2 will stay completely separate, balance, I mean handling the load. Okay, so this is something called HDFS federation, which is basically very much possible to 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 shard your data. Shard as in divide the data into multiple name nodes. Okay. Again, you might question that aren't we going into the same design, the design which we started, the one we call knife, right? Because maybe all of the data in the my data folder might become too high while my data 2 remains small, right? That is very much possible. Maybe the name node 1 is overloaded while name node 2 is not overloaded at all. Then you will have to think about some other folder segregation. All right. And this switching between the two happens at the client library level. It maintains something called mount tables, as in slash my data 1 is mounted from name node 1 and slash my data 2 is mounted from name node 2. So that kind of mount tables are maintained by the client library itself, and it can take care of that. Client library picks up this from configuration file. Yes, folder segregation will be taken by the client library. All right, any questions at this point? Now, Shravana's question is, in that the data node will correspond to both the name nodes or it will correspond to only one name node? No, data nodes will have the data from both the name nodes. Because data node doesn't really care much about this, but I need to check this part. It's a very good point. From the design, it seems that data nodes for both name nodes will be different. Okay, the data nodes for both the name node should be different, but I need to check this part. All right, as per my assumption, data nodes for both name node 1 and name node 2 would be different. Now Sanjay's question is, what is a cluster then? I thought one name node will have dedicated data nodes. Yeah. So most likely, all right. So Anandita is asking, can we repeat? Yeah, definitely. So basically, when there is a client library, when there is a lot of data which is not fitting into one name node, we can split it into two name nodes by defining the top level directories in something called mount tables. And this mount table definition is picked up from the configuration by the client library. And when the user asks for any data, say slash my data folder, then the request goes to first name node. If the request is pertaining to the second folder, the request will go to the second name node. All right. Now, this way we will be able to separate the data. Also, the data nodes for name node 1 and name node 2 will be, I think, different. That is something which I need to come back. Okay. All right, Sanjay. Now, Lloyd's question is, can we have federation and standby at the same time for all the federated name nodes? Yes, we can have federation as well as standby at the same time. Meaning, for each name node, there will be a standby. So, name node 1, standby 1, name node 2, standby 2, which means four nodes behaving like a name node. All right. Now Shravana's question is it only two name nodes or it can be more than it can be any number of name nodes. Alright? But keep in mind that the segregation can only happen at top level. It cannot happen at below than top level. Yes. It essentially means we are trying to scale out the name node. Alright? Now, a common question is, what does name node metadata? Name node metadata is metadata into the memory. The entire metadata is kept in the memory as well as kept in the file system. The the data in metadata is list of files. What are the various files? What are the various folders? For each file, how many blocks are there, which blocks, and which block is located on which data node, and also the file attributes such as access time, replication factor, file size, file name, and directory name. Transaction log is it records file creation, file deletion, etc. All right. So that's about name node. So you can see that this is how the metadata looks like. On the name node, there'll be file name like this, users as giri slash data and part 0 up to here. Then the replication mark, as in how many replicas we want for this particular file. And and where all is it located? And where all is this located? All right. So as an exercise, yes, we can delete a file in HDFS, Shavna. As an exercise, we will go through the our cloud labs and understand that how to create a. All right, let me first try to exit from here. All right, a little overview of our cloud labs. So here is Ambari. Ambari is an administration console which shows you the status of the cloud. You can see that HDFS space is this much used. There are 4 data nodes right now, and under HDFS, if you go, the name node is started, secondary name node is started. So you can see that we don't have a standby yet. Okay, we don't have a standby yet. We can configure the standby. Okay, and name node is consuming this much RAM out of this, and you can see all of this, and it shows you the complete administration overview. Okay, and the configuration, I'll show you a couple of things. Okay, we have used Ambari to install the cluster. If you want to set up your own cluster, Ambari is probably the easiest way to set up the cluster. You install Ambari server, and then you start installing Ambari agents on the nodes, and then keep on adding those nodes into the Ambari, and that's how you set up the whole cluster. All right. So you can see that the data directory on data node will be at this place. Okay, and this is where we are configuring where is the checkpoint directory, as in metadata will be kept in which part folder. Also, I'll show you a few more things. The total reserved space for HDFS is this much, and where is my block size? Do you see block size anywhere? It's here. Important factor, I have kept the default replica factor as 2. Okay, the default replica factor I've kept 2 because we are using solid state drives rather than the normal drives on our cluster. Therefore, it makes sense to keep a replica factor of 2. Also, we can increase it, but again, it will consume 3 times the space. This is our block size. Okay, what does this block size mean? These many bytes. If you divide it by these many bytes, meaning these many kilobytes and these many megabytes, I divide by 1024 twice. Okay, so you can see that we are having all of this configuration over here. All right. All right, now this is what we have. Now let me go to another interface. I will first open the my courses page. All right, now where is the today's session? I think this is the one. No, this is the one. All right, so here is your Ambari. Here is the hue, and we'll just copy the password, Hadoop 17. We can say Hadoop 17 and paste the password. Okay, so under here, this is hue. This using hue, we can interact with our Hadoop cluster. Okay, various components under hue. We talked about the okay. So here is the file browser. This is the HDFS file browser. Okay, you can create your folder here. All right, by creating from here, you can say You can say, let's say I'm creating my own folder. So you should create your own folder, because for the whole batch, this is the place, a single login right now. Okay, so that it's not a problem to find out where is my data. All right. So you can see that the here you can create your own folder, and under the hood, this is going into. So just now I created a folder. Will it Did it interact with as name node, or did it interact only with, sorry, did it interact with data node, or did it only interact with the name node? Anyone? I just created my folder here. Only the name node. Correct. Only the name node. Why? Because I'm just creating a folder. But the moment I upload something into my folder, this is my folder. Please create your own folder, because uh, do not do not bother with other people's file. So you can select a file. Let's say, what can I do? Which one is completely useless one? Okay, and let me just upload my Python sessions. Okay, or let me just upload this file. You can see that this file is getting uploaded, and here we have only this small file, 710 bytes. So for this, there'll be only a single block. All right, we can delete it or delete it forever. All right, we can upload a bigger file here, and then and also see the details about the file. Good. Or we can also see, all right, let's say we are talking about this particular movie. How come we are not having bigger files? Let me just try to upload a little bigger file. So we have, this is one big file, kinematic beta. It's, I think, uploading. Let it upload. All right. Where did it go? Let me just upload a little bigger file. I hope that it finishes on time. All right. So you can see that, and at the same time you can also log in onto the console here. You don't have to install anything. Okay, so you can copy the password, and then you can paste it, and here it is, Hadoop 17. All right, so these are the, this is not, when we say ls here locally, it means it's a local file. All right. Yes, that's correct, Sanjay. Okay, so here you can interact with the command line. So you can say Hadoop fs minus ls. Okay, so there are multiple file systems you need to understand. When we say Hadoop fs minus ls, we are talking to hdfs. Second, when we are talking through the file browser, we are talking to when we are talking to Hue, we are talking to hdfs. So either Hue or this command line, Hadoop fs, they interact with the file system. Okay, the usual one, ls, or uh, or, or the local one, because there are four servers. Each of these four servers also have their local file systems. Okay, so do not get confused. So there is this file system where you have just logged in. It's a local file system of Hadoop 3. It's a local file system of Hadoop 3. So here you will not see the folder called asgiri, but if you say Hadoop fs minus ls, you will see the folder called asgiri. All right, now let's try to do the hdfs block thing. I'm not sure how much time it's about to finish. Wow. All right, so let's pick up any folder. Let's pick up this pigudf.jar and say, so to find out where are my blocks, you can use the command called hdfs. Okay, so to find out where are the blocks, we can use the command called hdfs instead of using Hadoop fs. And let me just pick up this particular file. So all I'm saying is hdfs, is the font visible now? HDFS FSCK, give me the blocks, give me their location, give me their racks, and give me the information about their files. And this is the folder we are talking about. This is the folder we are talking about. Or let me just pick this one. This is looks really nice. And can I rename it? Can I rename it? Yeah. Let me just change it to a little cleaner one. Alright. So when we rename a file, are we interacting with HDF name node or data node? So you can press Control D and log out. Alright. So, alright, coming back here. This is the file we want to check how many data nodes it has gone to. Let's check. Okay. Yes, that's correct. So when we rename a file, we are only interacting with name node. We are not talking to the data nodes. Also, when we asked HDFS about this file which we had just uploaded, and you can see all the details. You can see that there are two blocks here. Sorry, there are two blocks here. There is a block 1 and there is a block 2. Okay, and this block is located on which computers? This computer and this computer. The first block has two copies, one here and other here. Okay, similarly the second block is having two copies, one here and other here. You can see the IP address. All right, so under the hood, this nice looking folder structure is splitted like this and spread across the cluster like this. Okay, so effectively we are utilizing all four nodes for storing this single file. You can see that first one is stored on 0.92 and 0.44, while second one is stored on 0.23 and 0.23 and 0.92. Okay, not really. We are actually utilizing only three nodes: 92, 44, and 232. Is everybody clear what am I trying to demonstrate? Anandita's question is, how can we create blocks on data nodes manually? You don't. Okay, whenever you create a file, it gets created uh, by the use of client library. In those cases, if you want to have your way, you will have to write a client library like Hadoop FS. The way we have this client library here, Hadoop FS minus ls. Okay, so to interact with Hadoop, you use the Hadoop FS command. To interact with Hadoop file system, you use Hadoop FS command. For example, if I have to copy something from the HDFS to local, I can say Hadoop FS copy from copy to local, and I give the file name and give the folder name. It'll copy from Hadoop to my local file system. This is my local. Local means this Hadoop 3. This is Hadoop 3 server. Okay. It's not HD. When I say LS, we are not talking to HDFS. We are actually talking to the mm, we are actually talking to the uh, Hadoop 3 local file system. So you can see that the file has been downloaded called movies.csv has been downloaded. Okay. Yes, when I say local file system, it is operating system's local file system. All right. All right. So Sarvana's question is, the second copy will be stored on the same rack, but it looks like it is on the different rack. Not really. There is actually only a single rack. Right now, I've not configured multiple rack. It's only a single rack right now. You can see default rack here. There's only a single rack right now. All right, I think I have missed some of your questions. Okay, let me just go through. If your question has been missed, could you just copy paste again, because it will be really painful for me to go through. Where can we get these commands and arguments? So if you say Hadoop fs, okay, if you say Hadoop space, if you don't give any command here, you will see the list of all the commands. There is a command called fs, there is a command called version. So if we say Hadoop version, it tells us the version of Hadoop. Okay, here we are using 2.4 instead of the latest version. Okay, and if you say Hadoop jar, it will execute your code on Hadoop, dist copy and all. Right now we are talking about Hadoop fs. Okay, this shows you that these are the various commands. Right now, the way we copied the data from Hadoop file system, in the same manner we could also copy the data from local file system to the Hadoop file system. Now you can see that Hadoop fs is fairly rich command. It can append to the file. It can append to the file here, and it can also concatenate. It can check, give you checksum, and there are everything you can do from the command line on HDFS. You can delete a directory, delete a file, move a file from one location to another, and so on. So you can see all of this just by typing Hadoop fs. So Sarvana's question is, if the replication factor is 2 and the same copy is stored in the same rank, and if yes, what will happen? Yes, it will be stored in the same rack. What will happen if the rack or data center goes down? The data get lost. Okay. Therefore, you should always keep a replication factor of 3. Right now, since our service provider has given us a guarantee and is keeping the backups of the servers anyway, we have reduced our replication factor to 2 from 3, because we are anyway using SSD. All right. So our hard disk failures probability is very small. So Sanjay's question is, so Hadoop FS is built on top of the local file system. That's correct. I can actually show you, if we talk about, if you remember, where were we? Here. So when we were going through here, it was saying that this is where the data nodes keep the data. Let's go to this folder. Oh, it doesn't allow me to do so. So maybe I can log in from another account, and I say ls and this folder. You can see that there is this folder structure over here. All right. So you can see current folder is there, then, all right. And these are the blocks stored. In the local file system, it is storing all the data. So it's basically these folders, directory under subdirectory, are storing the blocks. Okay. These are storing the blocks. Okay. So you should not touch this data. I'm doing it just for the demo sake. Okay. So this is where under the hood blocks are being stored on data nodes. Okay, as local files, small local files in the form of the blocks. Now you can copy back and forth between local file system and Hadoop file system using these two commands. If you want to control the permissions of these files, you can use chmod and chowner and so on. All right. I hope you got your answer, Sanjay. We can move back and forth between HDFS and a local file system using these two commands. All right, all right. So I hope you got your answers. Please explore by yourself. That will give you a far more confidence than me demonstrating the same thing. All right. Similar way, we could also demonstrate to you that we can increase the number of blocks, and the blocks will get copied on multiple machines. And also note that since every copy goes onto a fresh machine of the block, no two copies can be on the same block, same machine. If you try to set the replication factor more than the number of nodes you have, it will just keep on showing you that your file is unhealthy. Okay, it is under replicated. It will not be able to create more number of replication than number of data nodes. All right, is everybody on the same page? All right, before we move to next topic called compute engine, do you have any questions for me on HDFS? Any questions? Okay, so everyone's question is that, let me ask you this. I said that no two copies can be on the same machine. Okay, slash data node. Okay, agreed? Everybody is agreeing with this? No two copies of a block can be on the same machine, right? And we all understand, right? Why is it so? Because the purpose of backup is defeated if we try to backup on the same machine. Now, if you have three nodes or two nodes, can we have two nodes as in two data nodes? Okay, let me just put it clearly. Two data nodes or two machines running the data nodes. Can we have a replication factor of 3 on a file? Anyone? Correct. Yes. Even though we can change the replication factor to 3, it will keep giving us a kind of notification that hey, your file system is unhealthy. Your files are under replicated. You were promised 3 replica factor, but there are only 2 nodes, so there is no point in creating 3 copies. All right? So we can have, we can specify, but would be of no use. So we cannot have a replication factor of 3. We cannot achieve a replication factor of 3 on 2 nodes. Okay? It will keep on giving error. I'll show you that. I could have shown you that HDFS or Hadoop FS. There will be set REP. I would like to show you this. So I am setting the REP for this file. Okay. And what was the file name? I'll do that for a smaller file. Okay. So let's just pick up one file. Let's just say, let's just pick up a smaller file. This one. Okay. And go to the command prompt and we say Hadoop fs minus set rep 5 for user for this file. Okay. Now let's have a look. Pig udf.jar. Now you can see that let me just specify again user Hadoop 17. Now you can see that it's under replicated. Target replicas is 5, but it found 4 as replicas. Okay, you can see that it's under replicated, although it shows it healthy because the file is available completely, but you can see that Great. So this way we can keep this data, and we can keep on changing the replication factor for different files. If you have more important file, you increase the replication factor. But keep in mind that it would be of no use to set the replication factor more than total number of nodes available. So Sanjay, regarding yarn, just give me some time and you will understand that. All right? Good. Brilliant. Now let me just take the replication factor back to 3. Okay? So we discussed a number of things right now. Okay? We discussed number of things. First, uh, we try to demo you that this is your home page where everything will be available to you, including the webinar URL. And this is where you go to Ambari, which is admin interface, go to Hue, which is for developers, and console is again for developers. We have created a web-based console which you can use. And here is the password and login. You can simply copy it to the clipboard and paste it there. We have created it such that the password doesn't get recorded in the videos. Right? Next, we talked about that this is our terminal. We can use Hadoop FS command and HDFS command to interact with HDFS. If we want to administer HDFS, we use a command called HDFS. If we want to interact with Hadoop for copying and uploading file, then we use Hadoop FS command. Or we can simply use this beautiful browser which does Hadoop FS, Hadoop this and that under the hood and provides you this nice UI. Okay, let me just delete the file. All right, so everybody on the same page. Great, great. Let me, either you can do Control D and then close it, or you can type exit and then close the terminal. All right, so that's how it is. Next topic which we want to discuss, I think nobody has questions. So Anandita's question is how to give permission using Hadoop FS minus chmod. So are you trying to give permissions to the local one, or are you trying to give the permission to the HDFS file? If you want to change the permissions of HDFS file, you will have to use Hadoop FS minus chmod. Okay, and please read a little bit about, if you are not aware about Unix, read a little bit about how does permissioning work. What does it mean by 755? What does it mean by 700? Okay, that will be more comfortable to you. So then these things will not look like very awkward. So what does it mean by, how do you give permission in the form of, you want to give write permission, read permission, there is something called user, there is something called groups. Okay, all right. Great. So let's start with the computation engine part. Now we discussed about HDFS completely end to end, and now we are convinced that we have a great file system. Now, how do we process the data? Right now, we only talked about data uploading, data downloading, and what goes internally. but how do you process the data? That's what is covered in yarn, and then we'll cover in MapReduce. Okay, let's try to build things from bottom up. So first question to everyone: how fast can 1 gigahertz computer, 1 gigahertz processor sort 1 terabyte data? How fast can it do that? When I say sorting, sorting means ordering. And this 1 terabyte data is 10 billion names, 10 billion strings, with each being 100 character long. Okay, 10 basically you have to order 10 billion strings, 10 billion names, and the RAM you have is around 2 gigabyte. So I'm not asking you for an algorithm. All I'm asking is how would you order, how much time would it take? Just give me a number. Just give me a number. Lakshman says 4 hours, Suresh says 5 hours. All right. Jairam says 10 hours. Okay. Yes, it takes around 6 to 10 hours. It will easily go up to 10 hours. The question, so basically, there is what exactly is wrong with this? Okay, here we are only talking about 1 terabyte data. When we talk about petabytes of data, it is going to be really huge. Okay, so what's wrong with this is we need faster sorting. We might have bigger data than 1 terabyte for sorting. As well, along with that, you might have to do it very often. You might have to sort it very often. Okay, for example, Google is able to sort 10 petabyte of data in 6.5 hours using 8,000 computers. And this is a report of 2011, 8th September. Okay, so sorting being a very basic problem. Why I'm asking this question is because sorting is a very basic problem. Sorting, when we do a join in database, under the hood it does the sorting. When we do lookup, as in use the where clause, under the hood it relies upon sorting. If there is no index on the table and you are doing the lookup, it's going to be really slow. So when you create index on a table, under the hood it's doing the sorting. If you do a group by on a table, it's basically a sorting. Order by is sorting, it's ordering, right? So basically ordering or sorting is a very important algorithm, very important aspect of computing, to such an extent that it has become synonymous to computing in most of the world. Okay, and you will be surprised if I say things like that MapReduce is nothing but a grand sorting engine. Okay, MapReduce is nothing but a grand sorting engine. We will see that and you will understand what I mean by grand sorting engine. Therefore we I'm asking this question. So how do we sort bigger data in a lesser amount of time, and we have to do more often? Do you think increasing this processor to from 1 gigahertz to 10 gigahertz help? Anybody? If you do it, if you do it on a supercomputer, how fast will it be? Can anybody guess? It will be almost the same time. Okay? You'll be shocked to hear that, Yes, thank you, Ravikant. Yes, Ravikant says that it will be more or less time, same time. Yes. Why? Because our most of the time is gone into reading this data from the disk. If you remember our yesterday's discussion, it takes around 5 seconds to read a terabyte data. Reading 1 terabyte data itself will take 3 to 4 hours easily. Therefore, even whether you are using a supercomputer or a normal computer, the processing time would be the same. All right. So if this file of 1 terabyte data is lying on multiple computers, can't we utilize multiple computers to order the data in a really fast manner so that we will be utilizing these different computers in 1 terabyte data? Now you can imagine there will be 8,000 blocks, right? Around 8,000 blocks. And if you have 1,000 computers, then this 1 terabyte data can be done really fast by 1,000 computers parallelly, right? Correct. Thank you, Richard. So Sanjay is saying that India just bought 70 plus supercomputers, and I'm worried as they may be of not much use. Sort of, the time is gone when people used to feel proud about supercomputers. Right now, buying supercomputers is most like chest thumping and most like a PR that we are also technologists. All right. Although there are some algorithms which work still great on multi-core processors, which still work great on a single nodes, but most of the computing is trying to move on to the distributed one. All right. So Richard's question is that the question number 7 on the quiz: how fast can 1 gigahertz and 1 GB RAM do the 1 terabyte? You can choose 5 hours. Okay, because 5 hours is closest, and there is no fixed number to give the answer because it depends. So you can say the answer of this one might vary from 5 to 10 hours actually. Okay. All right, let me just put it 5 to 10 hours. That'll be okay. Because maybe some computers are able to do it in 5 hours if they are really really good and supercomputers. All right. Now how to get it done over the cluster? And that's where the MapReduce engine comes into play. Okay, we will start with Hadoop 1.0 description because that's easier to understand. Then we will describe the YANS architecture, which is Hadoop 2.0. Okay, so we'll start with Hadoop 1.0 and then we'll move on to Hadoop 2.0. Okay, so at the heart of the computation engine, it's again the master slave architecture. There is a job tracker and there are task trackers. Okay, now what does job tracker do? We ask job tracker to get the work done and it gets the work done via task trackers. Job tracker is like the supervisor of job shop. Okay, it's a job shop floor. There is a supervisor called job tracker. We ask this supervisor to execute things and it executes on multiple task trackers, and once the things get done, it responds back to you. In other words, you can visualize it this way: the client comes to the job tracker asks various task trackers to get the work done, and once these task trackers get the work done, they report back to the job tracker saying, we are done with it. All right. All right, we will continue this discussion on next week. All right. And yeah, so no worries, we will not try to hurry up. Instead, we will try to basically feel the distributed computing and the big data computing, because the concept what we are learning right now are going to be really really important in whole of the course as well as beyond the course. Okay. All right. Thank you very much and stay tuned. There'll be more questions as we go forward. All right. Thank you very much. Have a great day. Good night. Thank you, Sharna. Thank you, Sanjay. Thank you, Anandita. Thank you, Lloyd. Thank you, Lakshman. Thank you, Suresh. Thank you, Jairam. Thank you, Vidya. All right. Have a great day. Bye bye. Thank you, Karthik. I'm happy to have you in the session. This is probably the most interactive group I'm actually teaching right now, and I'm pretty happy with the performance of everyone. Okay. I'm thoroughly enjoying the session. Great, great. So keep interacting and keep learning. Thank you very much. Okay. Ravikant is saying if we are able to mention. So basically, the most important part here is that one is you finish the quiz, okay, and second is go. There is one more quiz here. So try finishing that quiz. All right. Also finish this Cloud Labs here. There is a document which I have written on what does it mean by Cloud Labs. Okay. So finish these two quiz by the next session. Also, some of this quiz may not be relevant to you, so you can stop at the point where you start with the uh, map reduce. Okay. So regarding timing, Suresh, timing changing will be very very difficult. All right. Okay, I'm completely comfortable with this time. All right, great. Have a great day. Bye bye. Yes, you can watch the videos, Richard, if you're going on vacation next weekend. All right. And for rest of the people, when we start the class, kindly help me, kindly remind me to start the recording. Okay. Sometimes I might forget because of various reasons. All right. Because some of the students may not be attending live. They'll be watching the recorded one. All right. Thank you very much. Have a great day. Bye bye.